In the hallowed halls of the Royal Swedish Academy of Sciences, a proclamation has been made that forever alters our understanding of the boundary between the tiny and the vast. The 2025 Nobel Prize in Physics has been awarded to a group of visionaries who dared to ask, can the strange, counterintuitive laws of quantum mechanics apply to objects we can see with our own eyes? For decades, the quantum realm was considered the exclusive domain of atoms, electrons, and photons, entities so small they defy traditional visualization. But the 2025 laureates have shattered this limitation. By engineering macroscopic quantum circuits, they have demonstrated that billions of electrons can act in unison, behaving not like a collection of particles, but as a single, coherent quantum wave. This achievement represents the culmination of a century of physics, moving us from the theoretical musings of Einstein and Bohr to a world where quantum superposition is an engineered reality on a silicon chip. This isn't just a prize for a clever experiment. It is the official recognition that the barrier between the classical world we inhabit and the quantum world we study has finally and irrevocably collapsed. To understand the magnitude of this breakthrough, we must first understand the problem of scale. In our daily lives, a ball is either here or there. It never exists in two places at once. This is the classical world. However, at the atomic scale, particles exist in a superposition of states, governed by probability rather than certainty. The great challenge of the 21st century was decoherence, the process by which the environment kicks a quantum system, forcing it to choose a single state. Usually, the larger an object is, the faster it decoheres. For a macroscopic circuit, decoherence should happen in a fraction of a nanosecond, making quantum behavior impossible to observe. Yet the 2025 laureates developed methods to isolate these circuits so perfectly that they maintain their quantum identity for milliseconds or even seconds. They created a macroscopic Schrödinger's cat made of superconducting metal where billions of electrons flow both clockwise and counterclockwise at the same time. This is not a simulation. It is a physical reality where the collective motion of a billion particles is governed by a single, giant wave function. At the heart of these macroscopic quantum circuits lies the Josephson junction, a thin, insulating barrier between two superconductors. This junction acts as a quantum gate, allowing pairs of electrons, known as Cooper pairs, to tunnel through the barrier without resistance. In the prize-winning work, these junctions were integrated into centimeter-scale loops. By precisely tuning the magnetic flux passing through these loops, the researchers achieved something once thought impossible, the flux qubit. Unlike the bits in your laptop, which are 0 or 1, these macroscopic loops exist in a state of 0 and 1 simultaneously. The sheer scale is what makes this a Nobel-worthy feat. We are talking about currents visible to the human eye, carrying enough energy to be measured by standard laboratory equipment, yet still obeying the delicate laws of entanglement. The laureates utilized the Aharonov-Bohm effect on a massive scale, proving that the electromagnetic potential can influence the phase of the electron wave function even in regions where the magnetic field itself is 0. It is a masterclass in precision engineering, requiring materials purified to the atomic level and designs that account for every possible source of thermal noise. Creating a macroscopic quantum state requires an environment colder than the deepest reaches of interstellar space. This journey takes us inside the dilution refrigerator, a marvel of cryogenic engineering that reaches temperatures just a few thousandths of a degree above absolute zero. At these temperatures, the thermal noise that usually destroys quantum coherence is frozen out. The 2025 Nobel laureates didn't just use these fridges, they revolutionized the way we interact with the circuits inside them. They developed ultra-low noise microwave interfaces that allow us to talk to the quantum circuit without introducing heat. Imagine trying to hear a whisper in the middle of a hurricane. That is what it's like to detect the quantum state of a macroscopic circuit. The researchers achieved this by using quantum-limited amplifiers, devices that amplify the signal without adding any uncertainty, as dictated by Heisenberg's uncertainty principle. This infrastructure is what allowed the team to verify that their centimeter-long circuits were indeed entangled, proving that the quantum realm is not a matter of size, but a matter of isolation. One of the most profound aspects of the 2025 award is the study of quantum phase transitions in one-dimensional wires. As these circuits become more complex, they encounter a phenomenon known as the quantum phase slip. This is where the topology of the quantum wave function changes spontaneously, a process that is essentially the quantum version of a knot untying itself. The laureates provided the first definitive experimental evidence of coherent phase slips in macroscopic circuits, a discovery that has deep implications for our understanding of the arrow of time and the nature of dissipation. By controlling these slips, they have created a new kind of electronic component, the quantum phase slip transistor. This device operates on the dual principles of charge and phase, offering a level of control over electricity that was previously unimaginable. This work bridges the gap between condensed matter physics and high-energy particle physics, showing that the same mathematical structures that describe the early universe can be found within a small, chilled chip in a basement lab in Stockholm or Zurich. While the 2025 Nobel Prize recognizes fundamental discovery, the practical implications are staggering. Macroscopic quantum circuits are the foundational building blocks of the first truly scalable quantum computers. Because these circuits are large, they can be fabricated using existing lithography techniques, making them much more practical than systems that rely on individual trapped atoms. But the impact goes beyond computing. These circuits are the world's most sensitive detectors. They can sense magnetic fields so weak they are generated by the firing of a single neuron in the human brain, leading to a new era of non-invasive medical imaging. They can detect subtle changes in gravity, allowing us to peer deep underground to find mineral deposits or monitor the movement of magma beneath volcanoes.